9.2 Equations of a plane in 3 dimensions. Now, the equation of a plane can be written in vector form. Now, what we will do is visualize what's going on over here. Let's suppose over here you've got a vector. Okay, and now let's suppose this vector passes through a plane over here. So you can see in red we've got the plane meeting the vector at a certain point. Okay? Now you can see currently there are an infinite number of planes defined so far, and we don't want that. We want one fixed plane. So how do we get one fixed plane? Well, you can imagine if we have, say, a vector which I'll show using this blue color, this restricts the plane so it can only move like this. Okay? But it's still unrestricted in the sense it's still not fixed to one place. So how do we get it to fix to one place? Well, for that, we'd need another vector. And if we have another vector, this restricts the movement of the plane, as we see over here. Now the plane is fixed. So let's just show that. You can see here, we have this vector and this vector, which are non-parallel, non-zero vectors in the plane. We have a position vector shown in red over here, and therefore this plane is restricted in movement. We have one unique plane. Let's try to draw on a diagram what we've just mentioned. So the first thing we need to do is draw a plane. We have over here something looking like this, and with planes we typically call these planes pi. Now let's suppose we've got a fixed point over here somewhere, and it starts off from the origin over here. It goes up, and then it goes under the plane, and then it meets at a point. We'll call this point A. And just to convince you that it looks something like this, let's go to GeoGebra and show you what I'm talking about. So you can see on GeoGebra I've got a plane over here. The plane's called P, and I've got this vector going to this point A over here, as you can see. Okay? And depending on which way you look at it, you can hopefully see, if we make this go through the plane, that it does go, if we can get this angle right, it goes under and then touches the plane over here somewhere. Okay, and typically when it comes to drawing a plane you don't need to show the axis. That just makes things more complicated. This is sufficient enough as a diagram to illustrate the plane and a point going through it. Now we do have these non-parallel, non-zero vectors in the plane, so let's just show those over here. We've got a vector here, we'll call this B, and we've got another vector over here, we'll call this C. Now let's suppose over here we've got a general point, call this point R. Okay, we'll put R over here somewhere. And hopefully you can see we go some multiple of b here and some multiple of c to get to here. So let's just try to show that. You can see here we've got the point R, we've gone over here some multiple, we'll call this multiple lambda, lots of b across, and some multiple of c, call this multiple mu, to get to this point R from this point A. And again, R is just a general point on the plane. So let's just join all this up. It goes under like so, and then we join it up like so. Okay, so here we've got R, and here we've got A. Okay. Now from this we can show the position vector of R. This will equal, so let's just write this down. The position vector of R, this is equal to going to A, so we add on A over here, and then we add on some multiple of B, and then we add on some multiple of C. This takes us up to this general point R over here. And this is how we would approach questions involving equations of planes. I recommend you all draw a diagram. And just as a point of benefit, you don't need to show these vectors B and C and their multiples either. Showing R and A is sufficient enough. So now, let's see what the notes say about all this. Suppose a plane passes through a given point A with position vector A, as we see over here. And if we let R be an arbitrary point on the plane with position vector R, then using the triangle law, R is equal to A plus AR. Okay, so here we have the vector R. And since AR lies in the plane, as we see in this diagram over here, it can be written as lambda lots of B plus mu lots of C, as we see over here, where B and C are non-parallel vectors in the plane and lambda and mu are scalars. And we've just discussed all of that. So the position vector R can be written as A plus lambda B plus mu C. The vector equation of a plane is R equals A plus lambda B plus mu C, where R is the position vector of a general point in the plane, A is the position vector of a point in the plane, and B and C are non-parallel, non-zero vectors in the plane, and lambda and mu are scalars. And if we go to the formula book, you'd find those formulas over here. Okay? And what we'll be doing is trying to use these formulas here. So the plane through non-collinear points A, B and C. So that just basically means A, B and C don't lie on the same straight line. This has vector equation R equals A plus lambda lots of B minus A plus mu lots of c minus a, which we can rewrite as this over here. So r is equal to 1 minus lambda minus mu lots of a plus lambda b plus lambda c. And alternatively, the plane through the point with position vector a and parallel to b and c has this equation here, r equals a plus sb plus tc. Example number 7, we have to find in the form r equals a plus lambda b plus mu c an equation of the plane that passes through the points a with coordinates 2, 2, minus 1, b with coordinates 3, 2, minus 1, and c with coordinates 4, 3, 5. Now, to do this, I think it will help to draw a diagram. So, we've got a plane, we'll call this plane pi. We've got the point A over here somewhere. We've got the point B, say, over here. So here we've got the point B, and we've got the point C over here somewhere. Okay? And we're finding the equation of this plane. So we've got over here the direction vector of A. Now, we could have the direction vector of B or C, it doesn't make a difference. The point is, if we use, say, B, then we'd have to find the vectors BC and BA. If we use C, then we have to use CB and CA as our direction vectors. But I'm choosing A, so I have to use AB and AC as the vectors, which will keep this plane fixed in space. So this is the vector OA, and it's connected to some general point R. So let's just put the point R over here. Here is the vector R. So let's just show everything. Here we've got A. Here we've got R. And our job is to find the equation of R. And if you recall from what we said previously, if we take the point A to be the position vector of a point in the plane, then we need to find out AB and AC, which will be the non-parallel, non-zero vectors in the plane. So, if we do that, you can see over here, AB and AC are vectors which lie in the plane. So we need to actually work out what those vectors are. So, AB, that's equal to OB minus OA. So we have the vector OB, which is 3, 2, minus 1, minus OA, which is 2, 2, minus 1. So if we work this out, 3 minus 2, that's 1, 2 minus 2, that's 0, minus 1 minus minus 1, that's 0. So this is the vector AB. And if we work out the vector AC, the vector AC, that's equal to the vector OC minus OA. So we've got the vector OC, which is 4, 3, 5, minus the vector OA, which is 2, 2, minus 1. So if we work this out, 4 minus 2, that's 2, 3 minus 2, that's 1, 5 minus minus 1, that's 6. Okay, so now we have direction vectors. Okay, let's just show these direction vectors on our diagram. We have over here the direction vector AB, which we'll denote as little b. Okay, and then we've got the direction vector AC, which we'll denote as little c. Okay? So now, when we come to work out the equation of the plane, using what we mentioned over here, OR, which is the vector form of the equation of the plane, that's equal to the vector A, so that will be 2, 2, minus 1, plus lambda, lots of the vector B, which is 1, 0, 0, plus mu lots of 2, 1, 6. Okay, so this is the vector equation of the plane, and it makes sense to go to this point R. Would have to go to A and then add on some multiple of B and then some multiple of C to get to this point R over here. So therefore, this is the vector equation of the plane. Example number 8, we have to verify that the point P with position vector 2, 2, minus 1 lies in the plane with vector equation 3, 4, minus 2 plus lambda lots of 2, 1, 1 plus mu lots of 1, minus 1, 2. Now, what we can do is write this equation as a single vector. So we have R, which is equal to 3, 4, minus 2 plus 2 lambda, and here we've got plus lambda, here we've got plus lambda, and then here we've got plus mu, then we've got minus mu, and then here we've got plus 2 mu. Now why am I choosing to do this? Well, if we want to show that P lies on the plane with this equation, we can set this equation equal to this, because remember R just tells us a general point on the plane, and if we get a value of lambda and mu which satisfies these three rows, then indeed P will lie on the plane. So we've got 2, 2, minus 1 equals 3 plus 2 lambda plus mu, 4 plus lambda minus mu, minus 2 plus lambda plus 2 mu. So if we take a look at the I components, we've got 2 equals 3 plus 2 lambda plus mu. If we take a look at the J component, we've got 2 equals 4 plus lambda minus mu, and if we take a look at the K component, we've got minus 1 equals minus 2 plus lambda plus 2 mu. Now, the way we can approach this is, well, if I call this equation 1, this equation 2, and this equation 3, if we solve two of the equations simultaneously, we'll find a value of lambda and mu. And if we substitute that into the third equation, and if we get the left hand side equaling the right hand side, because of the consistency in the values of lambda and mu, we can therefore conclude that this point will indeed lie on the plane. Okay, so if we solve equation 1 and equation 2 simultaneously, we can go to our calculator, and if we go to the simultaneous equations solver feature on our calculator, we have two equations, two unknowns. So if we take a look at this first equation, we've got 2 lambda plus 1 mu, and if we take this 3 over to the left hand side, 2 minus 3, that's minus 1. And if we take a look at the second equation, well, we've got 1 lambda minus 1 mu, and we've got 2 minus the 4, so that's minus 2. So you can see over here, lambda is equal to minus 1, mu is equal to 1. So what we will now do is confirm whether these parameters satisfy this third equation. So we will check in equation 3. So on the left hand side we've got the minus 1, and on the right hand side we've got minus 2 plus minus 1 plus 2 lots of 1. So here we've got minus 2 minus 1 plus 2. So indeed we get minus 1. And because the left hand side is equal to the right hand side, so let's just show that, because the left hand side is equal to the right hand side, we can therefore conclude over here that indeed P lies on the plane. Okay, so P lies on the plane. The direction of a plane can be described by giving a normal vector n. This is a vector that is perpendicular to the plane, and we see that in this diagram over here. One normal vector can describe an infinite number of parallel planes, and that makes sense. If you take a look at this diagram, we've got a plane over here and then we've got the normal to that plane, and you can see here we've got 2 parallel planes, and there will be an infinite number of parallel planes. So the normal vector on its own is not enough information to define a plane uniquely. So we can now move on to the Cartesian equation of a plane in 3 dimensions. And this can be written in the form ax plus by plus cz equals d, where a, b, c and d are constants, and a, b, c, the coefficients in front of x, y and z, that's the normal vector to the plane. And compare this to the Cartesian equation of a line in 2 dimensions, where we have ax plus by equals c. Okay, so there is some sort of a similarity over here. And you can derive this result using the scalar product, which you will learn later on. Now, happily for us, if you take a look in the formula book on page number 18, that is given over here. The plane through the point A with normal vector n equals n1i plus n2j plus n3k. This has Cartesian equation n1x plus n2y plus n3z plus d equals 0, where d is equal to minus a dot product with n, and this is essentially the scalar product. And if we match that up with what we have over here, instead of using a, b and c as the coefficients of I, j and k, the formula book instead has used n1, n2 and n3. And over here, if you compare with what we have in the notes, you can see here we have ax plus by plus cz equaling d. Over here we have a d on the left hand side, so that's taken into account if we move to the right hand side by including this minus. Okay. Example number 9. The plane pi is perpendicular to the normal vector n equals 3i minus 2j plus k, and passes through the point P with position vector 8i plus 4j minus 7k. And we have to find the Cartesian equation of the plane. First of all, let's draw the plane. we have the plane pi over here. Now we've got this normal vector to the plane, so let's just show that over here. The normal vector n is equal to 3i minus 2j plus k, and we've got this point P over here with coordinates 8, 4, minus 7. So let's just show this general point over here, and if we've got the origin over here, connecting this to this is this vector, which we'll call A. Okay? Now, having done all that, if we use what's in the formula book, that is the information we mentioned over here. First of all, if we work out what D is equal to minus a dot product with n. Okay? So D, that's equal to minus a dot product with n. So we've got minus, and then if we work out what a is, we have 8, 4, minus 7 dot product with 3, minus 2, 1. And to work out this dot product, it's really easy. Well, we still have this minus, we'll leave that alone for a second. And with the I components, we multiply those together. So we've got 8 times by 3. Then with the j components, we multiply those together. We've got 4 times by minus 2. And then with the k components, we multiply those together. So we've got minus 7 lots of 1. And then we add those together. So here, we've got minus 24 minus 8 minus 7. You can see here we've got minus 9. Okay? So, having said that, if we go back to what we have in the formula book, with the coefficients of I, j and k, those will be the coefficients of x, y and z. So, we can therefore conclude that the Cartesian equation of pi, well, we have, if we take a look at what we have over here, the components of I, j and k, we've got 3, minus 2 and 1. So we've got 3x minus 2y plus z, and then if you go back to what we mentioned in the formula book, we have plus d, that's adding minus 9, and this is equal to 0. So this is our Cartesian equation of the plane, and if you want, you can take this 9 over to the other side. So therefore you can conclude over here pi, that's equal to 3x minus 2y plus z equals 9.